I think we'll start. So today we are going to discuss unwrapping the guide wire, which guide wire to use when. So what is the value of guide wire in interventional cardiology? So many cases, complex cases, it is one of the main hardwares that is required for successful completion of some cases. And incorrect choice can not only lead to failure, but also lead to many complications. But especially this choice of guide wire is important in tortuous lesions, calcific lesions, where you require a side branch access, especially in those areas which have already been stented, wherever there is an angulated side branch access, and in some occlusive lesions, the choice of guide wire can make an important difference between success and failure. So basically, one has to understand that guide wire is really a product of some marvelous engineering. And it was got basically three components. One is the composition, second is the cover, third is the coating. So there are three components to any guide wire. One is the central core. That is the central core, that is the basic thing. And then at the end, there is a coil which connects to the central core. And everything is coated. Now, importance of everything is there. The importance of material is, if it is a very stiff material or a tensile material, then you have a lot of support. But at the same time, if it is a very tensile material, then flexibility will come down. So we have to draw a balance between how much support we require, and by support we mean support to the device that you are going to put. So if you are going to put a balloon over that wire, if you are going to put a stent over that wire, if you have to put an imaging catheter over that wire, if you have to put a rota over that wire, everything requires support. So if the material is tensile, if the diameter is more, support will be more. But what you lose is inflexibility. So it will be difficult to pass in some side branches if you have a very thick material or a very thick material. But color is important. So color is important or the tip is important. Because if the tip is made of a coil, then it is possible to maneuver the tip or maneuver the tip through lines. So if it is a coil, then it is possible to maneuver the tip through various bends or various branches. If it is a polymer, then it is even more easier to get into a branch or to get into bended lesions. If you have these polymers, then you lose on support. So, while one thing helps, other thing may be a downside. Then final thing is the coating. So, which is the coating which covers every guide wire. The coating can be, there could be a no coat, there could be a hydrophobic coating, or there could be a hydrophilic coating. Again, the coating makes the wire either stiff or slippery. So, if the coating is hydrophilic or polymer coating, then it can slip through many side branches, it can slip through tortuosities, everything. But there is no coating, then the friction will be more and it will not slip that much, although support will increase. So as you can see, everything is important. Now, what do we need in an ideal guide wire? Number one, of course, we need that the guide wire should be able to be pushed into whatever region that we want to go into. So the steerability of push transmission is, of course, as you might imagine, very important. Then the second thing that you want is there should be a one-to-one or torque transmission. So if you move it like this, the wire should move like this. So there should be a one-to-one thing. It is not that you move, but the wire is not moving. Then it is not torqueable. So then it is possible that you want to make the wire enter a branch, but if there is no torqueability, then wire will not move into the branch. So you require a 1:1 torque transmission. How do you achieve this 1:1 torque transmission? By having a unicore design. And I will show you what I mean by the unicore design. Means the core is extending from to the tip. If the core extends right to the tip, it is called a unicore. So a unicore design may help in crop transmission because ultimately you are moving the core. So if you are able to move the core and the core reaches till the end, then the end will also move. So unicore design is important, and also thickness of the core. Because if the core is thick and you move, then the transmission will be there. If the core is very thin, then there might be some loops and it will not shift. Then third thing is trackability. So trackability is of two types. One is trackability of the device over the wire, and the first is trackability of wire to go along the vessel wall. So if it is a tortuous lesion, you require the wire to track along that all the tortuosity. So for the good trackability, what you require is a loop friction. So the wires which are polymer coated or wires which are hydrophilic, because they have got low friction, they will be tracking. And there are other things also that I will show you. Then the fourth thing is durability. Durability means kink resistance. So as you might imagine, if you take a guide wire, normally a wire has a core which ends somewhere just before the tip, and it is connected to a coil. So you can see this is kind of a guide wire, and there is a coil here at the end. So durability means that you can bend this coil and make a particular shape of the tip. But durability is if you want to change back the shape of the tip. And if it is possible to do that, then it is a durable guide wire. But some of the wires, if you make a bend and then you are unable to bend them, then it is not a durable guide wire. Example is BMW. If you might be using BMW, if you once make the tip of the BMW, it is nearly impossible to get it back to normal and to make another kind of tip. So this is what is meant by durability. Then flexibility is, of course, the ability to wire to bend. So you need a bend at the tip. Overall, if you have to negotiate a side branch, then whole wire should be able to bend and go through that side branch if you are doing some PCI in a side branch region. So whole wire should bend. That is the flexibility of wire. It is also very important for minimizing trauma, because if the wire is flexible, then it will remain straight and it will cause a lot of trauma when you are passing different devices. Then, of course, mostly, as you know, that from where the coil starts, just before that part, there may be a shaping ribbon, and that whole thing from the shaping ribbon to the coil tip, to the tip of the wire, will have a radio opacity. And therefore, that radio opacity through which you can see the length of the wire, and that radio opacity typically is 30 mm. 3 cm or 30 mm. Typically, the radio opacity is this. But in some cases, there may be a different radio opaque length of the tip. For example, filter XT, it can be 120. So, the radio opaque portion of the wire is also very important, because that helps you see the tip very nicely inside the vessel. And that is the purpose of the radio opacity. You can see the wire going inside the vessel wherever it is crossing the lesion. Also, you can size your devices based on that length. So if it is a 30 mm, you can size your devices based on that radio opaque length. So that is important benefits of having a visible tip. And then there is something called a tactile feedback. Tactile feedback is, in PCI, everything you are dependent on your eyes. So your vision is being used for PCI. But for good PCI operators, there is also something called the touch sensation. So how the tip is behaving, if you can experience that feel of how the tip is behaving. If you push, then you feel the resistance. If it goes simply, you feel that it is sliding through. So that feeling of the tip is called the tactile feedback. And some wires, which are particularly non-coated wires, have the best tactile feel. But if you coat it first with a hydrophilic coat or hydrophobic coat, then tactile feel comes down. If you make it hydrophilic, then tactile feel even comes more down. And if you make a polymer tip, then the tactile feel is the lowest. So sometimes with polymer wires, it can be very dangerous because you don't feel the resistance and you don't know whether actually it is going through and causing perforation. So that is why you have to be very careful with polymer coated wires and also a little bit with hydrophilic wires because the tactile feel is less. So you don't get that feel that something wrong is happening and maybe we are penetrating the vessel wall. That feel may not be there with the wires which don't have tactile feel. So basically, again to summarize, what are the major requirements of a guide wire? Of course, one is push transmission, which is trackability, which is of course very important for transmission or for the advancement of the wire. The second thing is called transmission, that is to negotiate the bends, negotiate tortuosity, and negotiate side branch, go into the side branch. So that's really important. Then third thing is body support. The body support is the support that the wire gives when you push a device, whether you push a balloon or a device. So for bulky devices, you require more support. Then tip support. The tip support is also very important. Tip support is something that the tip, the resistance that the tip gives to a lesion. So if you encounter a lesion and if the tip just buckles, then it will never cross the lesion. But if the tip has some support, it will then bend sideways and go through the lesion. So that tip support is also very important because it allows the tip and search for the lumen, especially in total occlusion situations. The tip support becomes very important, and I will show you how you require the more tip support for total occlusions. Flexibility is of course very important, as I said, because if it is not flexible, then wire will be stiff. Then if you pass some device or something, then it may cause trauma to the vessel. So the wire should be flexible enough to take the shape of the vessel through which it is passed and not make the vessel take its own shape. And I will show you how this happens. If you have a stiff wire, then flexibility is not there, and then what problems you can encounter. Everybody understands visibility because you need to know where the wire is going. And tactile feedback, I already discussed with you. Hydrophobic wire or non-coated wires have the most tactile feel versus hydrophilic or polymer coated wire, which don't have a tactile feel. So everything good so far? Okay. Now coming to the components of guide wire, as I already told you, there are basically three components. One is the core. This is, let us say, the core. And the other is the coil tip, which is from here. And then there is something called a third thing is the top coat, which coats everything. So the core is normally made of either stainless steel, usually, sometimes retinol, but it can also be of different materials, plastic, even hybrid, like the run-through wire, which is a alloy, basically a hybrid, and PTFE core can also be there. But normally these kind of plastic wires are not very useful for coronary interventions because you do need some support and you do need some pushability. If you make a plastic core, then it has got very little pushability. It will go with the flow, but you will be unable to push it yourself. Coil tip, again, is very important, and it's generally made of alloy. Why alloy? Because you require a certain characteristic of the tip. You need the tip to have some strength, but also you need the tip to bend also when required. So where it is looking for lumen or when it has to negotiate a side branch, then it should be able to bend and make that turn. If you make only stainless steel, it will not make that particular bend. So then you have to have a different coil made of an alloy. As I said, normally of 50 mm length, and usually this part is opaque. The alloy uses platinum iridium, which not only gives the strength to the tip, but also gives flexibility, allowing it to take separate types of bends or or go into the side branch, and also allows the wire to be shaped by the operator. If you have only stainless steel wire, you can imagine how difficult it will be to shape that wire. So if you have a coil tip, that from where it is connected to core, you may be able to bend it. And so that is the importance of having a coil tip. And finally, top coat, again, as I said, the top coat depends on, it could be uncoated, which is generally not used, because if you use the uncoated wire, then there is a tendency to form thrombosis. So you don't really want that thing to happen. So you don't have an uncoated normal or coating, which is silicone or Teflon, which will not allow, which is biocompatible and not allow the thrombus to be formed, or which the point of hydrophilic coating is whenever it comes in contact with water, a hydrophilic coating will become a gel. And once it becomes a gel, it becomes very soft. And so you can negotiate the long distances of the vessels also. So if you are doing a distal lesion, a hydrophilic wire will help because it will have low resistance. It will help negotiate side branches. It will help negotiate tortuosities. So for all these situations, when you require to have lower friction, when you have a long length, you obviously cannot have a high friction wire because then it will not pass distally. Or if you have a tortuous wire, you cannot have a high friction wire. Or when you have to go through a side branch, then all these situations you require a low friction wire, and therefore you would coat it with a hydrophilic coating, which when it comes in contact with blood or water will become a gel, and then it becomes a very soft kind of thing. There are certain wires which are medium wire which don't have the same coil. So if you think you have to not bend anywhere and you have to do a straight lesion, then you might you might use a wire which does not have a coil. Because the purpose of coil is to take tortuosity, to take the bend, to take those kind of things. So if you have a classic straight lesion, then you might not require a coil. Instead, you could have a straight bend only. And now, effects I told you about the coating. Now, see, look, this is the general construction. Generally, the wire size is O14, and normally O14 goes till the end, but sometimes this O14 can taper. And those are the tapering guide wires. Example, crosset wire, where O14 becomes O10. Or a contact pro wire, where O14 becomes O09. So 009, a contact pro wire. So it will remain like this, and towards the tip, it will make a kind of taper. Importance of tapering wire, because where you require a lot of tip support, then what happens is you apply pressure on this big wire O14, but the tip has increased pushability because it becomes O14. And so it can penetrate through even tough lesions. So you might even penetrate through fibrous lesions. You might even go through the calcific lesion if O14 becomes O10 or O09. Therefore, for CTO lesions, this property may be used, only condition being that the CTO should not be a tortuous CTO. Because if it is a tortuous CTO, then you can easily perforate through this wire. So if it is a straight CTO, you could use a penetrating wire. So this is one part. The other part is, as I said, normally made of stainless steel. Why? Because the stainless steel gives good support. So always the stainless steel gives good support, and it has got a good pushability, and it has got a good torqueability. So 2-3 things are good with the stainless steel. It can be pushed easily. It has you can put a lot of devices over it, and it can even penetrate through certain things. So this is advantage of a stainless steel core. So if you require a penetrating wire, you cannot use any other material. You have to use the stainless steel. Then there are some metal coils. Normally, the coil is made of an alloy, tungsten, iridium, platinum, iridium, something like that. This coil is made. So this is, you can see, the coil starts from here, and you will have noticed, and before the central core and before the tip. And that is very important because if it extends here, then it will be very difficult to bend this wire. But if it does not extend here, you can bend it here. So this is to transmit the force. So ultimately, you have to transmit the force. You have to also have 1:1 transmission. And you also need the tip to bend. So how do you achieve this? Through this very interesting device called shaping ribbon. Shaping ribbon is connected from the core and it extends to the tip. It's just a ribbon. So this will allow your transmission to be there to the tip, but at the same time make it a bit flexible. So this is the engineering marvel that you can imagine, that the tip, the core ends before the tip, but it's connected to the tip. Clear? So this is the normal design of a normal guide wire. Now there are exceptions, there are changes, and we will come to that. So this is the usual construction. Again, 5 things are important in any wire, and that will decide what kind of wire it is. Number 1, the core diameter. As I said, if the core diameter is thicker, if this core is more, then it is more pushable. Number 1, it will give more support. Number 2, if you have to penetrate through the lesion, then it can do penetration also. So if you have a larger core, that is how it will have. The second thing is core material. If the core material is stainless steel or a very tough material, then again same things what I discussed will happen. When you have a core diameter, what you lose is flexibility. That is number 1. Number 2, shapeability is not there because it is very difficult to shape and then come back. So these are some of the things that you will lose. So 1 is core diameter, 2nd is core material, and that will decide. 3rd is core taper. And I told you, if it is a tapering core, then what happens? You can penetrate the occlusions also. Then the type of the coils or the sleeve. So these are the type of the coil. This is also very important because this is which will negotiate turns, bends, lesions, etc. and the strength. So these are the things, and you can see these are the parts. This is the coil, you can see, and here you can see this is the core ending before the tip, connect for shaping ribbon. You can see this shaping ribbon which is connected to the core and it extends to the tip to allow your transmission to happen. Otherwise, if it is not there, then you keep bending and there will be a gucha ban jayega and nothing will move. Actually, tip will not move at all. So that's why you require a shaping ribbon so that a transmission can happen, 1:1 transmission. So core material, as I gave you some example, stainless steel core is one type of core, and an elastic core, which is generally kind of nitinol. So a nitinol kind of core. So BMW has a nitinol core, which is not stainless steel. So that is why it gives you enough support, but not too much support. It can bend. You can always make the bend, and that because of the nitinol core. Otherwise, it will be difficult to make a nice bend. And here you can see what is the importance. Nitinol will give you, till membrane support, but it will not give you high support. Right? So for standard lesions, you use something like this, but for complex lesions, you generally require a stainless steel core. For a simple lesion, and run-through wire is another interesting wire, which is an alloy of a stainless steel and nitinol. So it's a stainless steel and nitinol alloy. This is not exactly nitinol; it is a type of something related to nitinol, elastinite, which is a trademark product. So I think same thing. Central core is the basic component of guide wire because it contributes to trackability, which means how the wire tracks along the vessel, torqueability, which means how it rotates, pushability, of not only the wire but also the device. And therefore, if the strength of the material is more and if the thickness is more, there is more torqueability and there is more support, less flexibility. So stainless steel has got more pushability, workability, shapeability, but less flexibility and more tendency to kill. Right? On the other hand, the Dura steel has got a better tip shape and retention. It's a type of steel which is Dura steel. Not much use, but there is a super elastic nitinol which gives more flexibility. But the problem is that once you shape it, then it gets deformed and it cannot be shaped back. And that is the problem with BMW wire, which contains this type of nitinol, that you cannot shape it back, and with prolonged use, it gets spoiled. So if you have to do multi-vessel things, then probably nitinol is not a very good idea. You have to have some stainless steel. Because stainless steel you can bend back, then bend again, then bend back. But nitinol, once you bend, then very difficult to bend back. That is the problem. It is durable, but less likely to prolapse. 1:1 transmission is also less with nitinol. So once you have to have, if you have to do CTO lesions, BMW is not a good idea, because it is made of nitinol and not stainless steel. For 1:1 torque transmission and pushability, support, everything you require is stainless steel. So if you have to do CTO lesions, you might have imagined that you would not use the BMW wire. So a little bit about unicore and dual core. Normal wire that we were discussing is a dual core wire, which the core ends before the tip and with a shaping ribbon. So this is the shaping ribbon, which connects the core to the tip. But this will, as you can imagine, it will have more flexibility with less 1:1 torque transmission, and also will give you less support and be less pushable, because the pressure that you are applying at the core is not directly transmitted to the tip, but it is transmitted through the shaping ribbon. But if you require those kind of characteristics, then you require a one-piece or a unicore wire. And that will not only have a better transmission, but also because the core is reaching the tip. So whatever is happening at the tip, that message or that sensation will come to you. So there will be a better tactile response or better tactile response feel with the unicore wires. So a little bit about coil transition. Normally, as you saw, coil extends for a long distance and covers the core for a long distance. And so that, kind of is a common thing. But sometimes you can, if you want to have a better torque transmission and you don't want to put a shaping ribbon, because shaping ribbon will give you some torque transmission that may not be 1:1 transmission. But if you really want a 1:1 transmission, at the same time you want the tip to be able to bend a little bit, then you can bend the spring coil into the core also. So that is one modification that can be done. So, and as I told you, diameter versus taper. Now, in the tapering, core may end before the tip, but if the tapering starts from a long distance, then what happens? Then what happens is that distal part you can bend a little bit more, because core will not allow you the wire to be bent. If the core is extending to the tip, same core thickness, then very small part of the wire could be bent. But if it is longer taper, then it will be track more and will have less prolapse. But shorter tip will give more support because more thickness of core is extending to the tip, and it will also have more torque response because more core is present to the tip, and therefore 1:1 transmission. The problem will be that it might prolapse. So sometimes you have seen you are trying to put wire and you push wire and suddenly you see the tip bends. So that will happen if you have a shorter taper. With a longer taper, this thing will not. Larger diameter is very easy. I told you the support. If you have larger diameter, more devices can be passed. A smaller diameter, bigger devices won't pass, but it will take the shape of the vessel very easily. So trackability will be better and flexibility will be better. Trackability means taking the shape of the vessel, and flexibility means taking side branches, taking tortuosities, etc. So those will improve if you have a small diameter. Now the second part is, of course, distal tip, and as I said, different types of tip. One type of tip you see where the tip does not reach the core does not reach the tip, rather the spring coil meets the tip. So this is the usual variety of guide wire. Most guide wires are like this. The tip is made by a coil. Second type, where there is no coil, but only polymer. So when it will be useful, a polymer coated wire. When any ideas? Rather than spring coil, if you have a polymer coated wire, where it could be more useful? CTOs, yes, but more importantly, acute total occlusions. Because there it will give more flexibility, it will track micro channels which are there, and it will pick up micro channels very easily. So where you want to pick up micro channels, you can then use this polymer wire. There was one wire called cross wire, which was basically a polymer wire, and you could use that for picking up these micro channels. Nowadays, Fielder FC wire is something like that, which has got a polymer thing, and you can cross it. And then there could be intermediate type where you not only have a coil, but you also have a polymer coating. Now, I already told you about the shaping ribbon. This is the core to tip for unicore wire. Now, good thing about it, you have better support, better tactile feel, better control, but less flexibility. If you have a shaping ribbon wire, you will have more flexibility and more shape retention, and you can have a radio opaque component to the wire. There will be less support and less control. Coils will have radio opacity, but will have less tactile feel. If the core extends to the tip, you will have more tactile feel. So there is one downside and there is an upside as well. Now, coming to the third part, that is wire coating. Coating, as I said, can be of three types. One is hydrophobic. Hydrophobic is biocompatible, but it retains water. And compared to uncoated wire, it will reduce the friction to half. So because that is why you don't use uncoated wire, but it will cause a lot of friction, it will cause a lot of aggression, it may cause even vessel injury. So you have to coat with something. A hydrophobic coat brings the friction to half. And it preserves the tactile feel, and obviously it can be palm easily. Hydrophilic wire, on the other hand, decreases the friction even less, and therefore allows for a better passage, becomes slippery when exposed to water or blood, as I told you, and doesn't deteriorate with the use because this nice coating is there of a gel on the wire. It will go anywhere without resistance, but problem is because it will go anywhere, it can enter the false lumen, it can cause large dissections, it can even go into branch, it can cause guide wire perforations, and it can stick to the catheter. So if you use hydrophilic wire to put in side branch, and if you want to use it in the gel wire technique, then hydrophilic wires, at least of older generation, were a problem because they can get stuck to the stent, and therefore when you are pulling out the side branch wire, this whole wire can even break. So that was the problem. Of course, the third type of wire coating is polymer coating, and this is again a non-thermogenic, is the least friction possible. Therefore, to improve porosity and to improve flexibility, and therefore ideal for picking, as I said, micro channels of acute total occlusions or the tortuous anatomy, where you want the wire to take the shape. And also there is something called star technique. I think we will discuss it when we do the total occlusion wires. So I'm not discussing it now. And the problem is that there is very little tactile feel. So you have to depend only on your vision. Easy to enter false lumen and cause perforations with these wires. Choice PT was a classical polymer coated wire. Nowadays you have some other polymer coated wires, and those wires can be very dangerous, especially in CTO situations, because they can cause perforation. So coming to some of the characteristics of the wire, as I said, number one is support. How much support the wire gives for passing a device, and how to measure it? At 100, when from the guide wire at 100 mm from the tip, you apply a press, and then see how the wire can bend. How much force is required to bend the wire? This is the support, lateral support or rail support. So, if lateral pressure is required to bend this wire at the from 100 mm from the tip, then rail support is better. And if less pressure is required, less force is required, then rail support is less. So, of course, it is important for improved deliverability. Sometimes the problem is that if there is a lot of rail support, then it may not go into the side branch, it may not take the vessel shape. So this is, as I said, lateral support or rail support. So there are basically, based on category of support, we divide wires into three categories. One is the standard support, which is anything between 8 to 15 gram that you require at that point to bend it. So 8 gram at 100 mm to bend it, then this is a standard wire. So between 8 and 15 is the standard. More than 15 is heavy duty, and less than 8 is light support. So for tortuous lesions, naturally you require to bend again and again. So you require a light support wire. For calcific lesions, you might require a heavy duty wire. So useful as a heavy duty wire is you can deliver bulky devices over it. It can give more support even through the stent struts or highly fibrotic or calcific lesions. And naturally, it can be useful when you are doing CTO because you require more pushability and more support if you have to do CTOs. So this is just some example. So balanced heavyweight lies has about 15 gram. Then there is something called an all-star wire, and many people use regularly. If you have to do calcific lesions or other kind of lesions, all-star wire, which is about 20, and then Grand Slam is 25, and Iron Man is around 50. This is a different thing, but these are the things. So first thing was rail support or lateral support, and rail support determines how easily the device will pass on the wire. So sometimes you have the situation, wire crossing, balloon not crossing, especially in CTOs. And that happens when wire does not have enough lateral support to allow the balloon to pass. Or you may have a situation, balloon crossing, but stent not crossing. And that is again dependent on the rail support. If you use a more heavy duty wire, then you may be able to pass balloon or stent as the case may be. But the second thing is tip load. What is tip load? The force needed to bend the tip of the wire from at 10 mm. Lateral support is 100 to, some people say 100, some people even take 150, 160. At that point, the force required to bend, and therefore that force may be different, but some people say 160 is the force or 100. So depending on that, but this is standard 10 millimeter from the tip, the force required to bend that tip. So that is the tip load. And what is the importance of tip load? Tip load is the ability through which the wire can penetrate into a fibrotic or stiff lesion. If the tip load is more, it is able to penetrate more. If the tip load is less, it is able to penetrate less. If lateral support is more bulky devices can pass. But if lateral support is less, then less bulky devices can. So this is the difference between tip load and lateral support. The classification of tip load is, there is something called extra floppy, where tip load is less than 0.6. So which means less than 0.6 gram can bend the tip at 10 millimeter. So this is the tip load. So extra floppy is tip load less than 0.6, floppy or the balance tip load less than 1. So between, let us say 0.7, 0.8, 0.91, you can call it a balance tip. Then the soft, when the tip load is 1 to 2. Then it is useful in acute total effusions. where you require, because if you are pushing through a normal vessel, you are only pushing through blood. So tip load required is very less. But if you are pushing through a thrombotic lesion, then you may require a little bit more pushability or little more ability of the tip to penetrate. And therefore, you might use a wire of 122, which is a soft tip wire. Then it would be medium. Again, in CTOs, in recent CTOs, you might want to use a medium tip load wire between 2 to 6. And in a chronic CTO wire, you might require a tip load of more than 6. So extra floppy wire with tip load less than 0.6 may be useful when there are multiple tortuosities, because you need the wire to take on the bends, the tip to take on the bends, and then the wire will follow. And more distance has to be traversed. And you are doing retrograde CTO, and I will come to that when I come to the CTO part. I will show you where this extra floppy wire like Xion Blue. Xion Blue is a classic extra floppy wire. It has got a tip load of 6. Another type of Xion Blue even has 0.5 tip load. So Xion Blue is an example. And then whenever you use a stop, then you have, as I said, acute total occlusion, recent MI, or a very fine fibrotic lesion. Medium is recent CTO, heavy is resistant CTO. I already told you. So the third thing is a torque response. And all these are bench tests that I'm describing. So these are not in the body, but they are done outside the body to determine. The third thing is torque response. So you take this kind of tortuous tube, and how much wire you can push through. That is the torque response. And if you are able to do 1:1 transmission, then it will take all the bends and it will go. So that determines how much 1:1 torque transmission is happening, and that is the torque response. Ideally, it should be 1:1, even in this kind of system. And these are the wires depending on their torque response. BMW, as you can see, lies somewhere in the between floppy line, and this is the ideal wire where you have 1:1 torque response. But as you can see, most wires are not ideal wires, and they don't have 1:1 response. So they have something less than 1:1 torque response. I think the deliverability part is also something where it's a transition. So where the transition happens, and that can make the movement of the wire easy or fail. So now, what are the attributes of a guide wire? Obviously, ideal wire is one which is successful. And what are the attributes of success? Generally, a success will be obtained when the tip load is high. When there is a penetrability, tip is tapered so that it penetrates to any kind of lesion. When there is no transition zone, so that there is a 1:1 torque transmission. When the wire is material of guide wire is stainless steel. Sorry, this is the coating material, but the material of guide wire is stainless steel. Then it will have more success. And when support of the guide wire is high, then again success will be more. But remember, whatever is there for success, same thing is a concern for safety. So when tip load is high, then safety is less. When it is a tapered wire, then safety is less. When material is stainless steel, then safety may be less. Although here, polymer wire is the most unsafe wire because you don't have a tactile feel, and it can move into false human, it can even perforate, and you may never know. So that is why polymer wire may be a more unsafe wire compared to a stainless steel wire. Then other thing is which wire to use when. So before the which wire to use when, we need to know what are the workhorse wires. So what are the prerequisites of a workhorse wire? Remember, could be either stainless steel, nitinol, or alloy. Normally, tip load needs to be less than 1. Normally, lateral support needs to be less than 10. It could be hydrophilic or hydrophobic coating, depending on where you are using. Normally, you will have a dual core wire where the core is attached to the tip by a caping ribbon. And normally, it will not be polymer coated because that makes the wire dangerous. So a constructive square will have these features. Guys, BMW or BMW Universal, run through Carino is another one. These are in the old wires, the Sally, Galileo wire, Hyper, or Star wire. Some people use it as I said, it has got a higher. The only difference is the lateral support of an all-star wire is about 20. But many experienced interventional cardiologists use it because they are generally doing some calcific, highly fibrotic, old lesions, and therefore many of them prefer all-star wire. It is not commonly a workhorse wire. It is mostly a wire used for those tough lesions. BMW run through are the commonest workhorse wires that we have. This is a BMW wire. You can see it is a elastinite wire with a tip load of 0.6. A BMW Universal may have a tip load of 0.7, but this one has a tip load of 6, 30 mm radio opaque length, 0.14 diameter. No taper. It could be, mostly it is hydrophilic. There is a shaping ribbon. There is no polymer, and as material is all, as I say, elastinite, one type of nitinol. So as you can see, the support is less than 10, it is about 8. Lateral support of a BMW wire is 8. So it comes in that category. Tip load is 0.7 of Universal. It has got a good balance, flexibility, and steerability, and a precise and achromatic tip. The other wire which has become more used now, even more than BMW, because the problem of BMW, what is the problem of BMW? Anybody? Sorry? Shape retention. Once BMW comes into a shape, it is impossible to get it back and to make it into a new shape. So if you are doing only a single lesion, then BMW might be useful. But if you are doing multiple lesions, RCA, many vessels, multi-vessel, multi-lesional PCI, then BMW is not a very good idea. Because once the shape gets bad, it will never become normal. One wire is a very interesting wire. It is a fusion of stainless steel and nitinol. So it has some features of stainless steel and some features of nitinol. So basically, this alloy is very useful, and you can reshape it also because of this particular property. Tip load is again same, around 0.6. Again, over 4 wire. Radio opaque is again 30. And basically same thing. But the only difference is that a run-through wire has got you can reshape it. And that is the thing. Only this particular wire is that there is a small optimal coating. So you have to be a bit careful with run-through. Especially, where you think, but normally you would not use run-through in a CTO lesions. Anyway, you would be using in the workhorse lesions, and therefore it is not a problem. Now, coming to tip shaping, how would you shape a tip? I think there is another slide. Oh, the slide. Okay. So basically, you have to look at 3 things. One is the entry angle. An entry angle is the angle through which the wire enters the lesion. So if this is the lesion, the wire enters through the lesion. So if the lesion is in a side branch, which is coming at 90 degree, then you need to make a more bend, a 90-degree bend. If it is more than 90 degree, then rather than a bend, you make a curve. Otherwise, it will not reach. So this is importance of entry angle, which is this angle. How much angle this makes? For 90 degree, you will have to make a 90-degree angle. Otherwise, you make a 45-degree angle. So first bend is called a primary bend. And primary bend is the length inside the lesion. So whatever the diameter of the lesion, you have that kind of tip bend. If it is a CTO, because in the CTO, there is, you can't see the lesion. So therefore, you make a only 1 millimeter bend. So that this bend can pick up micro channels. If you make a bigger bend, then you can never cross CTO. So either you don't make a bend, or you keep it straight, or you make only 1 millimeter bend in a CTO lesion. On the other hand, other kinds of lesion, depending on what kind of lesion it is, you can make the length of the bend. The third bend is the secondary bend, and that bend is important which is the diameter of the vessel that you are working at, because that will give you the support on that vessel. So these three things you need to know for shaping your guide wire. Yes. इस पे नहीं आ रहा यार, उसी में करना है, क्लिक करो तो चलो। इस पे नहीं आ रहा, इधर पे आ रहा है। Yeah. Okay, so I think, so you see, it depends on what part you have to reach. So this is the reach. So if the bend is like this, you see, so you have to enter into a side branch or something like that. Then if you make only one bend, you are unable to enter side branch, because you have to have one bend for the lesion and one bend for the side branch. But if you make two bends, then you may be able to enter into a side branch. Okay, I think now we'll have a break. I think Meena has to go also. So sir, can you say something? Then I think those who want to go through any exercise there. Okay?
So, I think everybody this type of the information, and I think today's lecture is most important. But once during the evaluation is first you have to cross the region. So successful crossing of the wire is 50% of the seeker. In selection of the guide you highlighted in the beginning. The proper selection of the guide and PCI is most important. Unless you do the experiment practice with the guide, something that very difficult to get here. We said that this is the long run can take competition, population, or technical evaluation, not be able to do this. Something that in the way to perform the specific attachment, which is very important to move out the practicing the guidelines, how to choose the guideline situation, we should do this guidelines for the successful PCI. But you want to get if you like complex PCIs, again, selection of the guideline more important. If you are using the motivator, then you want to begin, I think your guide should be. That's why you keep them. And one thing I think we will discuss how to change the how to change the mind into the when you think about the guideline, I don't know the but at the same time you can change the guideline according to this. I think this is a very good effort and continuous change the lecture so that we can have dedicated lecture. We have already said this is given this very much, and I hope everybody will be sure. The part with the very first so what will be teaching internally the advanced skills of the skills also take some better item that can be freedom. The lecture can be. The use and this is online, some other people also watching this. So I appreciate this, and I hope we'll continue this. And this is definitely, I think, all of us have to do the thank you very much. Thanks for it. Let's first look at the
Should we start?
कोऑर्डिनेट्स वो की जाएगा वो नहीं हो रहा था ना ये पीछे हो रहा है देखिए ब्रेकिंग सही है वो सही है रिकॉर्ड हो रहा है करके स्टार्ट करने कुछ तो क्या हाँ
So now we come to part 2, that is basically situations where there is importance of selection of guidewire. So we will see some cases and some situations, and before the situation we will understand what is the strategy. So coming to first type of lesions that we will deal with is the tortuous lesions. So you think among yourself what is the tortuous lesion? Again and again there are like bends. So what kind of characteristics would you require in a guide wire? So number one, guide wire should have a low tip load because the tip has to take track along the vessel. So tip load should be low, clearly. Also, rail support should also be low because it has to take those turns. Before the rail support should also be low. The third thing is you require it to have lower friction. तो दोनों थोड़ी देर बंद कर ले. Should be either hydrophilic coating, which has got a low friction, or even it could be even polymer coating, so that which has got even lower friction to negotiate and take shapes of the band. But the contradiction is that on this wire you have to push a device. So that device requires a higher support to negotiate those bends. So paradoxically, the rail support should be high for delivering the device. So this is the problem, that on one end you require a lower rail support for the wire to take those bends. On the other hand, you require a high rail support because ultimately you have to put devices through this particular situation. Third thing is, of course, good torqueability, because the bend is there, so you need to have 1:1 transmission, so that when you are trying to bend it in one direction, it bends, and then when it bends in other direction, that bend has to be taken. So good torqueability, and of course good scalability, which is the transmission, forward transmission. So these four characteristics are required. But as you can notice, there is a paradox in character 1 and character 2. And so how do you solve this problem? So one strategy is to use a balanced wire, which is got a low tip load, but a medium lateral tip load, or medium rail support. Maybe you could use a pure hydrophilic wire instead of a steel, or instead of a nitinol wire, which can have some of these characteristics. But the second strategy is that you use a low support wire to cross the lesion. And then over a microcatheter, you exchange with a heavier duty wire. So that way, you have already tracked and reached to the beyond the lesion. So that part is done with a low support wire and low tip load wire. But once you reach a certain point, when you cross that lesion, you put a microcatheter and you exchange with a heavier duty wire. So that is another option that you can take. And let us see how those options work out. Before that, what are the life support wires? And as I said, a general life support wire would have a tip load of lower tip load, but a lateral support of not more than 10. Because if you have a lateral support of more than 10, then it becomes a balanced wire or standard workforce wire. So you should have a wire of a lateral support of generally, actually less than 8. So BMW wire has an 8, pilot wire also has 8. So basically, it is a borderline light support wire. Generally, it is not a light support wire. This one, a sub-neo light, choice, floppy, and PT2 light. These were the ones. But currently, small blue wire is available, which I think is the best bet. Because as you must notice, the tip load is 0.5 and lateral support is 4. So both these lateral support is also low, much less than 8, and tip load is also low, much less than 0.7, 0.5. It's a hydrophilic wire. It has got a composite coil tip, and when we will do CTO, I will discuss with you the coil tip that Xiong Blue has. So maybe you will. And there is no polymer cover. Coil length is 180 millimeters. So it's a longer radio opaque wire. This you see. Made of high tensile, special type of steel, which is high tensile steel. This is the Xiong Blue wire. Radio opaque segment 30. That coil extends 180, but radio opaque segment only 30. High tensile steel. High tensile steel core, PTFE coating in the proximal part, but no coating here. There is a slip coat coating. So it's a hydrophilic slip coat coating where in contact with water it becomes gel. Tip load 0.5, radio density 30 millimeter, coil length 20 centimeter, 200 or 180, coating hydrophilic, over 1/4 inch diameter, and composite coil technology. This is a composite coil technology, but I will not spend time here because this is what we will discuss when we discuss the CTO wires. So this is an example of what you do when you take a high rail support wire like this. So you get these kind of things. See this thing. So this is like a special effect that you get to see when you use a high support wire. And there is this jaded appearance of the whole vessel because it gets straightened. The wire has got so much support that vessel, instead of taking tortuosity, the vessel takes the shape of the wire, not wire taking shape of the vessel. And that is the biggest problem. And this kind of thing, I will show you again. You just see this thing. So this is the normal shape. Once you put wire, then you get something like this. Looks like many dissections. And actually, it is a serious thing because if you keep vessel like this for a long time, it is not an innocuous situation. The person will start developing angina because actually it will behave like a lesion. So you can't be comfortable with this kind of position. Another thing, a tortuous RCA. Just wanted to show you, it's a shepherd's spoke RCA. There was a proximal cable occlusion. And there was tortuosity in RCA. You can see this tortuosity. You see this tortuosity in RCA. So this is the point that I wanted to make, that there is a tortuous RCA. So again, a balanced or a medium support wire used, Prof 100, which is a medium support wire. And even then, while I put cross, but states in the vessel, balloon is being put. Little difficult, but after dilatation can be done even on this kind of appearance. And but the problem is once you this wire, multiple tortuosities and those kind of things appear, and it started causing problem to the patient. So ultimately, process was removed, and then another wire was used, which was a lower support wire. Exchanged by microcatheter and a lower support wire passed, and then finally the procedure was done. So this is that wire and final position. This is another third case, tortuous RCA. So I will go again. I'm sorry, some of the ones are not running. I think they were old ones, so some are not running in this program. Anyway, so this is the tortuous lesion and at the bend. So the region was crossed with a Xiong Blue wire. You see, this is the cyan blue wire, and you see that it takes the shape of the vessel. Instead of vessel taking shape of the wire, this wire is taking shape of the vessel. And after that is the exchange with balanced heavyweight wire, like microcatheter, and lesion dilated with semi-compliant balloon. Just understand this, and then the stent is nicely positioned, and again, final run, and you will see that it's like nicely stented. So this is that exchange strategy I was talking about. Use a lower tip load light duty wire, cross the lesion, it will take the shape, then exchange with a middleweight wire. If those jagged appearances come, then that is too high support. You have to again exchange with a lower support wire, and then over that try to pass the balloon and stent. So that is, I think, the correct strategy. Now, another special situation, not tortuous, but lesion at a bend or lesion beyond the stent struts. So that is a special situation. Now, what you require in this case, again, you need the tip to go through, negotiate this particular bend, cross over that stent strut, and therefore you cannot have a higher tip load wire. You need a floppy tip load wire, which can be shaped properly, because ultimately you shape it before putting the wire inside, and then you know that where the stent started and what angle the vessel is coming, and based on that angle you shape your wire properly. So here you require a wire that can be properly shaped and also having a good range support, because ultimately you have to pass a balloon and a stent across the stent strut. So you will require a huge better support. So the critical thing here is that the wire should be shaped so that you don't have to try to make that bend, because the wire will not bend. If you take a heavier support wire, it will not take that bend. So you have to shape it, pre-shape it, and that is the key for these kind of things, especially in a two-stent strategy. If you want to enter through the stent struts or in a provisional stent where side branch goes away and you need to cross that stent strut. So here, very important to see the orientation of the side branch, and based on that orientation, according to that angle, you shape the tip curve. That is the critical part. If you are unable to shape that curve and you take a heavier support wire, that wire will not take shape. Again and again, it will go here and there. So you have to make a proper shape, and you have to have a wire with good range support and obviously with the good torqueability. Because once you enter the vessel, then it should again transmit your force and go further in the side branch. So good torqueability, good steerability or pushability. So all these characteristics are required. One good wire is Asahi Grand Slam wire. You can see tip load is in the floppy range between 0.7 to 1.8, and range support is very high, 39. BMW range support is only 8. BH2 range support is 15. All-Star range support is 20. But this one has a high range support, 39. And a very small coil, so that once it bends, then rest of the wire can follow that coil. So very small coils. These are the characteristics of this interesting wire. Another wire that is useful for side branch is something called a bigger wire. And I don't know if anybody has heard of this name, because this is not very widely available. We had this wire from at NIMS. So this wire has actually, I will show you this wire, has a series of combination of bends. The wire itself has got these bends. So that is the thing. And so what happens is, once you move the wire, the tip either may align with the vessel wall or it may come out of the vessel wall. So suppose I will show you this one. And so you can, if you push the wire, then it tip moves away from the vessel wall. If you push more, then it again touches the vessel wall. It's like a snake. It's like a snake forcing on the vessel. And depending on, if you push, the snake either bites the vessel wall or moves away from the vessel wall. So, and that helps in many situations, because then you can negotiate through different kind of bends and different kind of struts also. And there is also another special wire called a regatta wire, which has got a special shaping ribbon. And that shaping ribbon, as you know, improves the flexibility. And therefore, the tip can be highly flexible. It is already, the tip is made in that way that it can negotiate the bend. So this is this regatta wire. And as you can see, that already the coil, there is a bend imparted to the coil. So very nicely, if you take a conventional wire, what happens is if you try to push it, it will collapse to the stent strut. And then this you might have noticed, when you push, it collapses and everything comes out. But this wire is already bent. So once you push it, it enters like a, let us say like a hood of a snake inside the side branch. So this is a special kind of wire that's again not available widely, and it's available only for specialized use. So here let us see. These are three frozen frames. AN1 7F similar approach was used. It was a severe calcific tortuous RCA lesion, which was dilated with a non-compliant balloon. 2 drug-eluting stents were tried, but the stents could not pass. And then after the stents, this balloon was non-compliant balloon was tried, and you might have noticed that after PCI, many cases you do the PCI, you plant the stent, and then you try to put a non-compliant balloon inside that stent, and that balloon does not go in. And you try again and again, especially if you are using a Oxford balloon, it does not go in. If you try a new balloon, it might go in, but an Oxford balloon refuses to go in. The same situation happened. Nicely stented, but you wanted to post dilate a certain part, and balloon wouldn't cross. And so what was happening was that the stent was not properly deployed, stent strut, and stent strut was malopposed and was lying inside the vessel lumen. And when you were trying to pass the balloon tip was hitting that stent strut and unable to cross that stent strut because it was there was a bias and the balloon bias, and balloon was hitting the stent strut, and it could not go beyond the stent strut so that you could go beyond and then you could dilate the vessel. So this was what was happening. So they tried to improve the guide support, use the guide liner. This is a guide liner, but it's still guide liner could not help. It was still getting stuck. So therefore, this wiggle wire was used. That one I was telling you about. Now the beauty of wiggle wire is that if like this is the vessel wall, this is the stent strut which is protruding in. You put a normal wire or balloon, this wire gets stuck here or balloon gets stuck here, cannot go beyond this. But if you use a wiggle wire instead of hitting this, if you push, it will move away. And then you can pass your balloon and you push further, then it will again come back. Because it is like this. So depending on where the wire is touching, if you push more, it will just come out. And if you push again, it will go in. So this use of this wiggle wire, this whole procedure was done, and this distal stent strut was negotiated, and PCI was done. Ultimately, it could change the wire bias, and then once the wire bias was changed, the wire could cross beyond, and the balloon could actually cross beyond the stent strut, and then you could post dilate it. So what is this wiggle wire? So you see, this is the wiggle wire. So again, microglide coating, hydrophilic coating to make it a very flexible wire. These guys. So you push, this guy can come here. You push more, this will go this direction. Push more, it will come this direction. So let me say start here. This is start here, which is occluding. If you push, it will move like this. And it can cross the stent strut, and then you push more, then it will again come back. So that is how this wiggle wire helped in this particular case. So I hope it is clear. It's clear to everybody, right? Good. So you see, same thing. This is there is a experience where this crossing the stent struts, this particular operator achieved 100% success using this particular wire. the wiggle wire. And this is, you see what I was trying to say. So if there is something here, let us say kind of stuff here, just put it in, and if you put the hit this kind of stuff. And it will not cross. But this wire, it will like turn like this, and then you can cross, and then you can reach. So this is the way this wire will work. And that is how you can cross whenever there are problems. So coming to second type of lesions, which are the calcific or highly fibrotic lesions. What are the characteristics required? Of course, you require a higher tip load because you need to, move across this fibrosis lesion, penetrate through that lesion, or take a different direction through that lesion. So you require a higher tip load and also a higher range support. So my recommendation is you can do an escalation technique. You can start with, let us say, a balanced heavyweight wire, which has got a lateral support or range support of 15. And if it doesn't help, then you can move to grand wire, which has got a support of about 40, 39 support. If it's not possible, then you could use this special Iron Man thing, which is more than 50. So this wire has more than 50 lateral support. So this is the currently available wire. Our strategy could be we use this bigger wire again. So if there is a calcium somewhere and the wire is again striking that and is unable to cross that, so you can penetrate this calcium and you require a very high tip load for that. And also it becomes very risky because if you try to penetrate this calcium, very high tip loads might be required. Maybe you request through 20, tip load of 20 to crack through this calcium. And suppose it goes beyond and it perforates the vessel, very high likelihood of perforation also. So a risky wire. So other thing is, again, if there is a calcific thing, you just want to take a different direction. And you take a wiggle wire, and wiggle wire, when it stucks the calcium, you push and it moves away from the calcium and it enters another lumen. And through that lumen it goes. So you can again use a wiggle wire for this kind of thing also. And this is the Iron Man wire, as I said. So you see, BSW lies here, and then comes this one, which is this is the all-star wire. This is the all-star wire. This is the Iron Man, and this is the Grand Slam, and this is the Iron. So Iron Man, as you can see, has the highest support. And so for practically all kind of lesions, you can use this. Again, I don't think it is available at your place. There was another wire, Mailman, also, but that wire is now obsolete. The only wire that is available now is the Iron Man wire. And for very calcific lesions, you want to do rota, etc., those kind of things, Iron Man wire can be used. So these are the heavy duty wires, as I said. Common is BHW, which has got a tip load of 0.7 and lateral support of 15. So this was the wire that we use in tortuous lesions also, because a balanced heavyweight and a low tip load or a floppy tip load. But then this aside Grand Slam, gain tip load 28 with lateral support 39. Iron Man, as I said, more than 50, 65 lateral support and a tip load of 1 and a hydrophobic wire. 4 to tip, so that you can transmit your force and you can transmit everything. So 4 to tip wire. So which means no coils and no polymer. So this is one example of unicore wire I was talking about, or core to tip wire. So this you can use. Other things are now platinum plus Mailman, they're not available in India now. So they are like only in US available in US. So I think this is clear. But another interesting thing that you can do is sometimes when you don't have many labs won't even have a Grand Slam wire. Does SMS have Grand Slam wire? You have Grand Slam. But many labs may not have Grand Slam wire, or sometimes Grand Slam wire is not enough, and then you don't have Iron Man wire. So there, sometimes you could use a rota wire. And rota wire is also 2 times floppy and extra support. And this extra support wire is very interesting because it has got a lot of support. So some of the calcific lesions, normally in a calcific lesion, what you do is if you want to do rota, you take all-star wire commonly or some people have used BHW wire. If it goes, then fine. Otherwise, Grand Slam wire. After putting the Grand Slam wire, you cross, you put a micro catheter, and through the micro catheter, you can pass the rota wire. Problem with the rota wire is that if it is all steel wire, and there can be a wire bias, so it cannot be, because there is no coil in this wire. So problem is that it may not take bends. So if it is a straight calcific lesion, you can pass this rota wire. If there is slight tortuosity, rota wire may cause perforation because it does not take the even slight bend. So there you have to use a heavy duty wire with a coiled heavy duty wire, like let us say Grand Slam or BHW or All-Star wire, and then put a micro catheter, and over the micro catheter cross with the rota wire. But sometimes when straight calcific lesion is there are no bends, absolutely straight, then you could even directly use a rota wire. So here is a case, severe calcific lesion, RCA, you can see this practically whole RCA is case. So it was crossed with BMW first, unable to cross. So microcatheter used here, microcatheter getting stuck, unable to cross. Improve the belt support, shifted from JR4 to AL2, still unable to cross. And what did was that slightly, used a balloon to open the tip, and through that pass the rota wire. And through that direct wiring with the rota wire, it could cross, and the rota is done. And then after that, after rota, then with microcatheter exchange with another wire, or you could put another wire if it is nicely open, then balloon, and now nicely prepared lesion, ballooning different parts. Post dilating after rota is very important. And then this is the final picture. So you can see that because the was straight, and that is why this magnified view was done to see whether there is any tortuosity at all. And because there was no tortuosity at all at that point, that is why rota wire was taken, and that is how it was done. Coming to the third category, acute total occlusions. Now, what is the characteristic of acute total occlusion? Normally, in a vessel, you have to just pass the wire on the edges of the wall through blood. But when there is total occlusion, instead of blood, there is thrombus. So naturally, you require a wire with a higher tip load, anything more than floppy. And that is why you could use the soft wire, which has got a tip load of between 1 to 2. So you could use a soft wire with a hydrophilic coating, because you don't want a wire to have resistance. And this kind of wire can easily pick this, basically penetrate through the thrombus, and you can do. Although many cases you could do with any 1/4 wire. I don't know whether if you electively use fielder SC wire for crossing these acute thrombotic lesions, because most of them you would still cross with a regular wire. But sometimes when there are some little bit of fibrosis there, and it's a like old MI where the thrombus might getting organized. So if it is particularly out of window period MI you are trying to do, where thrombus may have been organized, you might require a wire with a higher tip load. And that is when you would require a soft wire. So these are some of the wires for acute total occlusion. And as you might see, that tip load is between 1 to, generally 1 to 2, but you could go up to 4. The cross wire entry, remove cross wire, produce this cross wire is no longer available. Which you don't want the wire to make any bends, because there is a thrombus that you have to negotiate. So you might take even without coils, wire without coils, only polymer coating wires. Normally you would use a spring coil wire. Fielder SC, as I said, is a classical wire for this situation. What I mean is, many cases you would do with even BMW or N-through. But if it is out of window period MI, where thrombus might be getting organized, then you might have some difficulty crossing with BMW wire. wire, which interestingly has 110 millimeter spring coil. So you remember it has got a 110 millimeter in the and tip load of 1.6. So exactly between 1 and 2. So this is the kind of wire that is most suitable in this situation where you have organized thrombus. So case 69-year-old female, complete heart block, presented with acute inferior MI. So presented local hospital for 12 hours coming out of window period. And so thrombus getting organized, but you have to do this procedure because patient is in cardiogenic shock. So you can't say out of window period now nothing to be done. You have to do something because patient is cardiogenic shock. As you can see, pulse, blood pressure is 50 systolic. Complete heart block present, pulse rate of 30. This is the situation. I think it is not running, but there was a thrombotic cutoff here. You see in RCA. So whisper wire was tried, and ultimately, whisper wire, as you see, is one of the options, as I showed you earlier. Whisper wire, tip load of 1, and polymer coat, and tip load of 1. So whisper wire was used here. And then it could cross into, this is actually an old case. At that time, Fielder FC was not available. That's why I think this is not running. This is a bit older case, I think. I think what it is about at least 12. No. 2012. So you see that this particular wire, whisper wire, this was and the difference between whisper and Fielder FC wire is that whisper wire is cheaper. Fielder FC wire is more expensive. So a whisper wire was used to cross this, and so now the fourth situation is a recent CTO, less than 6 months. So a recent CTO, again in recent CTO, difference between recent CTO and older CTO is that in recent CTO, many micro channels are present. And in an older CTO, there is just fibrosis and calcification. So earlier CTO is to be treated differently. So here, now what you want is that you have to pick these micro channels. So you require something like medium tip load, standard brain support, and a hydrophilic coating. So again, the wires can be same, whisper, pilot. There was another very interesting wire, cross wire, that is thermo cross wire, which is now not available. But Fielder FC wire can again be used here because it can pick up micro channels. Other option is you could use a medium tip load wire like crosset wire, which is penetrating wire also, and can penetrate through the fibrous tissue and enter the micro channel. Persuader, Provia, and Miracle, all these types. Intermediate level Miracle wires, 3, 4, 5, and 6. Another case, 61-year-old hypertensive, diabetic, 1 month duration, ECT, ST segment depression, echo showed 40% regional wall motion abnormality. Again, now CTO, now it seems stupid to try using BMW, but BMW was used and as expected enters into subintimal space, but then Miracle 4.5 wire is used. So Miracle is, I will show you when I show you CTO wires, but Miracle wire has, this is the tip load. Miracle 4.5 means tip load of 4.5. Miracle 6 means tip load of 6. Miracle 9 means tip load of 9. Miracle 12 means tip load of 12. There is another wire called Conquest Pro or Conquest wire, which is like Miracle wire. It has got a tapering tip. The tip of Conquest tapers to 010. But then again, same sizes 3, 4.5, 6, 9, and 12. But 12 tip tapers to 009. So Conquest Pro tip, 20 Pro tip goes to 0.009. So Miracle wire you can use when there is a slight tortuosity. But if there is no tortuosity, like maybe LED, you could even use Conquest Pro wire, Conquest wire or Conquest Pro wire. That is the difference, because Conquest has got a tapering tip and it can perforate. So here, parallel wire technique used, BMW left in the subinterval space, crossed with the Conquest, crossed with the Miracle wire, then this subinterval wire removed, and then through the contralateral injection check if the wire is in the true lumen. Because always, if you do CTO, it's a good idea to do contralateral injections, and through contralateral injection, it was proved that the wire is in the true lumen. Then lumen dilatation done, and finally the PCI was done. Now, another thing is sometimes when you need to measure, so you have 2-3 lesions, you want to measure exactly how much length of the lesion is there. Then you have something called a marker wire. I just wanted to let you know that this wire, as you can see, there is a marker here. The marker is 5 millimeter in length, and 15 millimeter non-marker area, then another 5 millimeter length, then 15 millimeter, and then 20 millimeter marker. So this marker wire you can use in a vessel with multiple lesions, and you can measure those lesion lengths and then appropriately select your stent. So what are the complications associated with guides? Workhorse wires, the major complication is that you are unsuccessful. Normally, it's a soft wire, lower tip load, lower lateral support, so not much pushy wire. So the most problem that you can do is that you may fail in your procedure. But the heavy duty wire can cause the straightening artifacts I showed you. And I will show you one more straightening artifact, especially in tortuous lesions. You will see those straightening artifacts, and they can even cause symptoms. Polymer wire, as I said, less tactile feel. So you could end up with perforation. Or if you gel this wire, if you gel a polymer wire and in the stent, doing provisional stenting. So in a provisional stenting time, you stent branch you cross with a polymer wire, deploy a stent on the main vessel, and when you try to remove this polymer wire, this whole polymer can come out and the wire can fracture. So that is one other problem. With light support wire, the main problem will be inability to deliver bulky devices. Heavy tip load wire, because tip is heavy, it can cross through the vessel wall and can cause dissection or perforation. And penetrating or tapering tip wires, again same problem, you can have perforation. So these are some of the complications, and I will like to show you some of the complications. So this is yeah. So this is a guide wire induced perf that can happen, and this is the totally occluded right. So wire is being passed, and with a long, you can see it's a filter wire, which has got a longer radiopaque thick, but once it crossed, you can see the perforation. So this is a common thing that you can have with a penetrating wire or with a higher tip load wire. This is what can happen, and this is the perforation. Ultimately, deploy a covered stent, and the perforation sealed. Final result. Another thing that can happen is, as I said, when you put a polymer wire in the side branch and you stent the main branch doing a provisional kind of stenting, so provisional anti-bifurcation stenting, and once you deploy the system and you try to pull that wire is not coming out. And if you pull too much, it might get broken. It might fracture, polymer may strip off, it can fracture and break and lie inside the side branch, as has happened here. So entrapment can happen. So this is something that you need to be careful about. And this is that straightening of the bend is called the accordion effect. And it produces these pseudo lesions. When this is the shape, if you put a medium or any kind of wire, then this is the shape of the wire and there are these possible lesions, which is called the Claudian effect, like this thing, Claudian, and this can cause symptoms. Patient can even have death on table because of this effect. So it's a serious thing. So once you diagnose it, what you do is put a microcatheter and change with a lesser heavy duty wire. So lesser duty wire. So this is what you need to show. It's gonna sound of
हेलो हेलो इसमें से लोग गायब हो गए थे तो मैंने अभी स्ट्रीम स्टॉप कर दिया तो मैंने स्टॉप कर दिया तो मैं बोले खत्म हो जाएगा करके अभी कोई भी नहीं है सब चले गए एक ही पर्सन है वो भी अपन बस हाँ ठीक है